at CENTOGENE. I spent my whole career in AI, starting in the age of GoFi, good old-fashioned AI. And I've been working in using AI as an assistant services for supporting humans in learning and working, whether it's at schools, university, but also smart manufacturing, Industry 4.0. And 3 years ago, I joined CENTOGENE, going into life sciences to build up the AI department at CENTOGENE. And now in my presentation, I'd like to give you an overview on how to use AI for diagnostics and R&D in rare diseases. So it's really a rough overview. It's like serving a plate of appetizers. And if you have additional questions, more interest, then later in the networking sessions, we can of course talk about it. So for this audience, I don't need to spend much time to talk about why AI, but still I'd like to bring across one thing that I learned. AI is an engineering discipline that gives a set of methods and technologies. It's one thing, but from my experience, the main benefit of AI is really to enable innovation as a means to innovate business, and AI is really one of the enabling technologies. And this innovation character of AI, it's really native in artificial intelligence. And this is why I like this very old definition of AI so much, that AI is a study of how to make computer do things at which at the moment people are better. And that points at this ongoing innovation in AI as a field itself. And it's also a bit the dilemma of AI. So on the one hand, AI is an incubator for many innovative technologies. But then once AI solves a field, then it goes to computer science. It becomes a separate subfield of computer science. So we have seen this over and over of the history of AI. And we have seen also over the history of AI, how AI creates values by automation, by improving quality and efficiency, by generating insights from data, and by enabling new business models. And what's so important if you want to really make successful AI is this combination of the IT department, and those business units, the domain experts that we aim at supporting. Now you really have these cross-sectional teams in order to implement successful AI solutions. And AI can also create value for rare diseases. So why are rare diseases a worthy topic to tackle? Well, even though they are called rare diseases, they are not rare at all. 350 million, in estimation, are affected by rare diseases, and many of which of those are children. And even today, in the age of digitalization, of AI, we have this diagnostic odyssey, that it takes more than 8 years for someone suffering from a rare disease, more than 8 years to be correctly diagnosed, which is of course tragic, especially considering many of those affected are children, and many rare diseases show the symptoms very early on, and 30% of children suffering from rare diseases will not see their 5th birthday. So it's really whatever you can contribute in order to improve diagnostics and in order to develop therapies, it's really a worthy goal. And this is what we are working at here at CENTOGENE. So our mission is to be the one player to go to for rare diseases. If you're a patient or a physician and you have a patient potentially suffering from a rare diseases and you want to get the diagnosis, but also if you're a pharma company and want to enable new treatment or improve your clinical trials. And very central of CENTOGENE is the bio and data banks that we have established over the years. CENTOGENE was founded in 2007. So it's a database consisting of more than 600,000 individuals, meaning of their biomaterial, dried blood spot cards, but also other biomaterial, and then the data that we generated from that, genetic data coming from panels, whole genome, whole exome, metabolomics data, more and more transcriptomic data, phenotypic information giving the clinical symptoms, and socio-demographic information. And we use that on the one hand to provide the best possible diagnosis for patients, but then also working together with our biopharma partners for drug development, for clinical development and market access. And AI is a central part in all what we are doing. Let's first look at AI in the diagnostics processes. So this is a typical diagnostic process. If you do genetic diagnostic, so you receive the samples. We use dried blood spot cards, which are really easy to send around by mail worldwide. And physicians send us these dried blood spot cards together with the clinical information. And first of all, of course, you have to capture the clinical information, what you get. And despite us offering digital platforms, many physicians still prefer the good old paper way. So they send us the dried blood spot cards together with paper information, which we then have to digitize now, because everything else later is digital. So we have to digitize information. That's solved basically. So you can use any cloud service to digitize the paper information that you get. Then you want to extract most of it. Also nice area to apply AI on. And there it's getting already a bit more difficult because, well, on the one hand, we have predefined forms, which are easy to access and to extract information from. But in addition, we get paper documents in any format, now uncontrolled. And then it gets really difficult still today for AI to find those parts in this free form text that are potentially relevant. So on the one hand, you extract most that you can get with respect to the clinical data. And then you have, of course, the genetics pipelines that then start the sequencing, extracting the DNA. And there, of course, in the very first step, you can use AI. We implemented one service recently that looks at anomalies in the lab processing, because even in the best labs, from time to time, errors happens. So we use anomaly detection for finding those probes that are samples that are potentially wrong, that don't behave like all the others. And one problem there is that you luckily have very few samples. So if you have a very unbalanced data set, because 99.999 whatever 9% of the samples are processed correctly, very few are carry mistakes. So we then were able to, by looking at a few artificially produced contaminations, we are able to spot the patterns, and now we are able to generate synthetically anomalies, which we can then use for training the algorithms. And then once you have sequenced the DNA, you want to identify those of these millions mutations that everybody carries that are the disease causing, that are relevant with respect to the phenotypes. So we have methods for variant prioritization, identifying the relevant mutations. And there, the lesson we learned over the AI as a field learned since the renaissance of machine learning, namely that algorithms is one thing, but the data is the other thing, and potentially even more relevant. This we learned also, and we are able to outperform our competitors in identifying the disease relevant mutations because of the very unique data set that we have. And then, of course, when you do the diagnostics, when you have the physicians, our medical expert looking at the information that was extracted from the clinical information and at the identified variants, and coming up with the final report, you can use AI to support in various ways. And then also in the last step, in the curation step, so the step where the data is once more looked over before it enters our biodata bank, there also one can use AI, and sometimes one can use even good old-fashioned AI, because there we had standard operating procedures describing very precisely what the curators were supposed to do, because it has to really perform to the highest qualities. And we had these paper documents that described the human expert, okay, check this, and then do this or that. And if you have already the way how to solve a problem, if you have all the knowledge already specified, then there's no need to use machine learning. Then you would use what was formerly called expert system. Today it's called business rule management system. So you would use a formalism that allows you to encode this domain knowledge as quickly as possible with the lowest effort. Now, if you use one of these systems, it's a low-code environment, you can very quickly capture the domain knowledge. So if you have knowledge already, no need to learn it. Actually, we tried machine learning on that problem, but because of the very imbalanced data sets that we have, our POCs did not yield better results, or the machine learning based POCs did not yield better results than the formalized human expert knowledge. So AI can be used at several steps in the diagnostics process, but even more interesting is, of course, using AI for generating insights for drug development. And you all know about the complexity and the cost associated with developing a drug, the many years it takes, $1 billion of money that you have spent, and the high risk of failure. And I won't go into detail on all phases. I'd like to focus on the very first step, the very early R&D, where you try to identify the targets, those genes that might serve as the object to interfere with a potential drug at a later point. And why is it so relevant to identify a good target? Because many studies have shown that the more you know, the better you understand about the disease pathology, the more you understand the genetic causes of a disease, and if you have a drug on which gene it will, or which protein it will fix upon, which pathways it will affect, the more you know, the less the probability that you will fail in the later clinical trials. And this is, of course, also relevant for rare diseases, because many rare diseases are monogenic. So you have one mutation that causes the disease. So it's a slightly simplified, but still very, very complex disease pathology, but it makes the overall picture slightly more simple. So it's definitely worth identifying the best possible target and understanding most out of it. Just to mention lead identification, so building up substances that then attack a target, lead identification optimization and the support of clinical trials is, of course, a very, very hot area currently for AI and drug development. But if I would go also in detail on these points, then Musin would be really unhappy, because then I would talk for yet another hour. So we focus just on the very first step. So how can AI contribute to identifying the best possible targets? Well, you can use AI to add layers and layers on information to the data that you get from your experiments. And then with this additional layers and information, this context knowledge, you will generate deeper and deeper knowledge out of the data that you have. So typically you start with a list of genes that you get either from the literature, that you get from genome-wide association studies, or maybe from doing transcriptomic analysis. So you have a list of relevant genes, maybe 200 out of 25,000 of genes. And this is already nice because it like restricts the search space. But then you can do the next step. You can look at diseases in networks, how they correlate with others. So you do the step from a single gene to networks of genes. Then you can add additional information on top of these genes that you have identified. So you can use information from curated literature, you can add information from experimental data, public databases. So you add more and more pieces of information, scores to the targets. So you can use a score that gives you the novelty of a potential target, or you can have a score that gives you the support from the literature on a given target. So you add information onto your genes. And then you can use that information that you collected, that you brought together in the networks that you were detected, to identify, well, genes of networks that somehow belong together, that share potentially a function with respect to the disease pathology. So you do the step from a single gene to annotated genes to sets of collection of genes that you look at together. And the last layer of AI, so to speak, is that you reach the state of causal models. You do the step from correlation to causality, so that you really have a model that clearly specifies the dependencies and interrelationships between the relevant actors for a disease. And then you can use that model for scientific reasoning. And for me, one term that captures what we are doing here quite well is the sample efficiency. Now you want to extract the best possible, most possible, the maximum information out of the data that you have, out of the experimental data. You add layers and layers, you create the maximum value of these, out of these single data points. So we look at a few examples. Most diseases are complex. So it's not just one gene or one reason that causes a disease. And even in the case of rare diseases where you have a single mutation that's really disease causing, there you see that patients with the same mutation have different levels of severity on the level of the phenotypes. So these such called modifier genes. So there must be something still different in their genetic profile. So diseases are caused by an interaction of the genes, and there are many ways how to do the step from a single gene that is of interest to networks. Here I just cite one of many different methods. So you start with data from single genes coming maybe from transcriptomic data, and then you look at what are the genes that are co-expressed together. So you do the step single gene to networks, and these networks then can serve as the basis for various different other methods that allow to infer the function of unknown genes, for instance. And the standard technology today to enrich data to get the most knowledge added to your data that you have are knowledge graphs. So knowledge graphs are an established framework that allows to integrate different relevant data sets in a meaningful way. It's used in many areas, not just health, finance, everywhere, among all industry, but also very prominent in the health industry. And also we build our own CENTOGENE, our own knowledge graph that integrates various sources of information on proteins and genes, on pathways, on metabolites, on drugs. So you have like one integrated framework that you can then use for various purposes. You can run different algorithms on top of it to make the best use out of the data. So you can use it for querying and visualization. So instead of visiting several databases one at a time, you have one query that retrieves all the relevant information. You can use classical graph algorithms to identify central actors, identify relevant proteins. You can identify other potentially relevant genes for a specific set of genes. You can identify significant pathways. And then you can even do the step to make assumptions about information that's not contained in these graphs. Now, because all these graphs are, of course, incomplete. Our knowledge about biology is incomplete. So you cannot get all questions answered by direct queries. So you can use methods that look at patterns in the graph to make predictions about unknown properties. And then the final step, as I said, is the move from correlation to causality. There, one method comes from systems biology, disease maps that really very precisely capture the relevant actors and their relationships in such a detailed way that you can use it as a scientific model and assess scientific hypotheses. So here in the background, we see one disease map that we created, a CENTOGENE focusing on lysosomal storage disorders, our main area of expertise. And these detailed models allow you to overlay patient data, experimental data, and see how it's reflected in this map, but it also allows you to do in silico experiments to see what are the effects of changes to the pathways.
Of course, sorry to interrupt you. You have 5 minutes and two very important questions. If you wish to allow the questions, or how do you wish to finalize?
Okay, I have one more slide and then we'll finish.
Thank you.
Okay, and then AI can also enable new business, and this is really I'm so happy about that example because it's really the ideal journey of an AI-enabled product. It started with a proof of concept. Our biomarker R&D department came with a question that they wanted to discover relevant metabolites more quickly among 7,000 that they measure. So we built a small machine learning system to do that. Then they had the next problem. They wanted to look at not just at one measurement, but at all the measurements that they ever did together. So the system extended and extended. And the final system that we are using currently for internal ID, AI plays a small role, but very central role, but it's now part of a whole framework. Now this framework we will disseminate, we will make it available as a product for our pharma partners. Okay, so to conclude, rare diseases, a highly interesting topic also for the usage of AI. We've seen examples of how to use AI to improve diagnostic workflows, generating new insights and enabling new business model. And all this was done with really an AI department that was built up in the last 3 years, 10 people. So even with small teams in relatively small companies, you can achieve a lot. Okay, good. I hope that was interesting. Let me open the chat.
Yeah, let me make it easier. If Calvin from Bayer, I give you microphone, Calvin, can you raise your question because it's too long to read it. Calvin, thanks.
Yeah, can you guys hear me?
Yes.
Yep.
Okay, brilliant. So my question is basically about data because Carsten, thank you very much. First of all, thank you very much for the presentation. Very, very interesting. And for all the data that you have collected, I'm wondering because for this technology drift, right? Like you have different data type. For example, like even among NGS, you can have like different generation and then different data quality. And now we are having like single cell sequencing and all these new technology. So how do you guys deal with this technology drift in terms of analyzing your data? Because I think that would pose a lot of issue for your AI and machine learning algorithm to adapt, right? Because every single sample or every batch of the sample could be different, and you have this slowly migrating batch effect from all your data. So what is the long-term strategy for CENTOGENE to deal with that? Because I think this is not only about sequencing data, but it actually happen in all types of data, even like for health data that we collect from devices. This also is a very great problem. Like, what is your plan?
I get your question. So on the one hand, you have the raw data format, so to speak, but then you have the higher level of data on which you do the reasoning. So you're interested in the variants that were identified. You don't care so much about whether it's come from a panel with, or what the precise technology was used to generate the variant data. So for many applications, the relevant data is in a more, the data relevant for doing the reasoning is on a higher level of abstraction. So that's fine. But of course, if you do now the step to introduce a completely new technology like single cell, which is really gives you different results than if you look at the data that we get from dried blood spots, then it's of course a challenging question, different question. Yeah.
Thanks a lot. Thank you. So the last, let me check the time. I think we have just 2 minutes. Another question, Bagmeet. Can you just start with your question, Bagmeet? Bagmeet from MDM.
Sure. Thank you, Mushin. Thanks, Carsten, for the very interesting information on the pipeline. I'm very happy to see that you have some causal modeling also in your pipeline, because I think that will add very interesting insights. And my question was, how resilient is the pipeline to missingness in your data? I'm assuming for genetic data, you would need very high quality, accurate data. Would you be able to add some real world data on top of it and sort of derive insights?
I mean, you have missingness of data on very different levels, and especially if you're talking about rare diseases. So we have some rare diseases where we have hundreds of cases, and then we have some rare diseases where only have 5 or even less cases. No? So there's a missingness comes already from the rarity, and there's no general answer. It's a difficult problem to solve, but in the end, we support human experts who look at the results. Now, and the human dimension then can, of course, cope with these kind of difficulties more easily.
Okay, and then that is also true for the causal modeling part. there is some resilience there.
There's some resilience there, but of course, the causal models, they only also give you mostly what's reflected by the current state of the knowledge. No? So it allows you to put the data that you have into the context of what you know today, but you will see some misbehavior, and then you have to adapt the model appropriately. So however detailed these models are, they will never capture the whole complexity, but they still give you like a line of thought, a direction in which to go to.
Okay, makes sense. Thank you.
Thanks a lot. Thank you. Thanks a lot, Carsten, for this amazing presentation. There was another question, but you can reply that question on the LinkedIn page or on the chat